There are some important concepts related to irrational numbers. So let us revisit irrational numbers. There are some important theorems to learn. First important theorem is, let t be the prime number, p divides a square, p also divides a, where a is a positive integer. Let the prime decomposition of number a be the product p1 into p2 into p3 into so on till pn. Where p1, p2, p3 till pn are primes, not necessarily distinct. If a value is that, then by squaring it becomes p1 into p2 into p3 into so on till pn, multiplied to p1 into p2 into p3 so on till pn. Now observe it. Suppose p divides p1 into p2 into p3 into so on till pn. It means that this p should be any one among this p1, p2, p3 till pn. It should be any one. If p divides that, then p also divides p1 into p2 into so on till pn, multiplied to p1 into p2 into pn. Therefore, if p divides a, this implies p also divides a square. The next theorem is, prove that root 2 is an irrational number. If you remember, in class 9 we had done, in one of the methods, we had done long division method and we had expressed in decimal form, and we had observed that the value of root 2 is neither terminating nor recurring, so it was considered an irrational number. In class 10, we have to prove root 2 as irrational by the method of contradiction. For that, let us assume the root 2 be a rational number. By the definition of rational number, we know that it is in the form of p by q or a by b, where a and b are integers and b is not equal to 0. This a and b, these are co-prime numbers. The meaning of co-prime numbers is their highest common factor is 1. Let us square this. So squaring on both sides, we get 2 is equal to a square by b square. This implies 2 times of b square is b square. Two divides a square. This implies 2 divides a. By the previous theorem, we have seen b divides a square, then b divides a. Now, if you take the value of a to be some multiple of, then 2b square will become equal to 2m whole square. It becomes 4m square. Here 2 divides b square. This implies 2 divides b. So considering these two, we can say that the highest common factor is not equal to 1. Thus it becomes equal to 2. Therefore, it contradicts our assumption. It contradicts. Therefore, root 2 is an irrational number. We have another theorem proving root 2 as an irrational number. It is explained here with some of the steps. The first step is we will consider root 2 to be a rational number. So by the definition of a rational number, it is in the form of a by b, where a and b are integers, is 1 to 0. In this case, a and b are co-prime. The meaning of co-prime is their highest common factor is 1. If you square on both the sides of this expression root 2 equal to a by b, we get 2 equal to a square by b square, which implies a square equal to 2 times of b square. Let us name this as equation 1. A square is divisible by 2 because it is written as 2 times of b square. This implies a is divisible by 2. Observe, a square is as a factor 2. Then a square is even, then a is also even. Think 4 is an even, then 2 is even. Look at third step. A is divisible by 2. So we can write a as multiple of 2, say 2m, where m is a natural number. Let us substitute this equation 3 in equation 1. We get 2m whole square equal to 2b square. This implies 4m square equal to 2b square. So b square is equal to 2m square. Again we have b square divisible by 2 Therefore, P is also divisible by 2. Since A is divisible by 2 and B also is divisible by 2, they have the common factor 2. So the highest common factor is 2, which is not equal to 1. It contradicts our assumption because the highest common factor of A and B must be equal to 1, but we are getting it as 2. Let us apply the same logic and prove root 3 as an irrational number. In the first step, we'll consider it as a rational number. So let root 3 is equal to A by B, where A and B are, what are they? We need to mention here integers, and B is not equal to 0. And A and B are, co-primes. Now squaring on both the sides, we get 3 equal to A square by B square. Therefore, A square is equal to 3B square. Let's name this as equation 1. A square is divisible by 3. So A is divisible by 3. Now let us take A as multiple of 3. So 3m, where m is a natural number. Let us substitute equation 3 in equation 1. We get 3m whole square equal to 3b square, which implies 9m square equal to 3b square. This is 3 times. So 3m square equal to b square. B square is divisible by 3. So b also is divisible by 3. From equation 2 and equation 4, we get A comma B, their highest common factor is 3. This contradicts our assumption. Therefore, root 3 is a rational number. Can you develop a proof for root 5 as an irrational? So first we have to consider root 5 as rational. This implies root 5 is in the form of p by q, where p and q are integers, q is not equal to 0, and the highest common factor of p and q is 1. Now you square on both sides. We get 5 equal to p square by q square. This implies p square is 5 times of q square. P square is divisible by 5. This implies p is divisible by 5. So let p be some 5 times of some number, say 5m. On substituting in p square is equal to 5q square, we get 5m whole square equal to 5q square. So 5m square equal to q square. Therefore q square is divisible by 5. Therefore q is divisible by 5. This implies the highest common factor of p, q is 5 not equal to 1. This contradicts our assumption, therefore root 5 is an irrational number. Revisiting rational numbers and their decimal expansion. Here we are going to decide whether the given rational number is a terminating decimal or a recurring decimal. Say, for example, I consider 35 upon 50. Is it a terminating decimal? Here we are not going to do actual division, but then we are going to express this denominator as a product of prime. This can be written as 2 into 5 into 5, nothing but 35 upon 2 into 5 raised to the power 2. Always remember, whenever the denominator is purely in the form of 2 to the power of m into 5 to the power of n, the decimal expansion always will be terminating.